So hi everyone. Let's wait till 6:10 and then we shall start. Let's wait for a few more people to join. Um, Hi Vinay, hi Anubhav. Let's wait for 5-6 more minutes. Then we shall start. By the way, from today onwards, we will start revising everything. So I'll be going through this book written by the instructor of the course. For as promised in last class, I will be revising just in case, uh, because by the end of this syllabus, by the end of this classes and videos, it becomes very hectic for you to revise from start. So I'll be giving you a brief revision, and then you can go through the in-depth content by yourself. Let's wait till 6:10. This is week 8. I'm starting now. So till now, I'm sharing my screen first of all. Okay. Uh, okay. So in week 1, we got through the introduction of everything: Python, Network X, what is social network. Then in week 2, we started the basics of network. This thing, what should we call this? Networking and all. So we will be revising week 1 and week 2 today. Before that, we also discussed the assignments. So week 7 assignment and week 6 assignment, I think, needs to be discussed. So let's go to week 7 assignment. I think this was discussed or not. Let me check which assignments we have done. Week 8, yeah. Week 8 deadline should not be over yet, I think so. Yeah, week 8 deadline is still not over, so week 7, I think week 7 is pending. So we are discussing week 7 assignment. And assignment solutions will be released by this week till week 7. Then 8, 9, 10, 11, 12 will be released after week 12 is done. So first question is, link prediction can only predict missing links in graph's current state and not forecast future links. That is wrong, because in future there will be some new connections in the same nodes, and we don't know if they have not seen before yet. So whatever missing links are there, they are all obviously coming in future. So yeah, so it is false. In dynamic networks, a link prediction problem must account for addition of new nodes. True. So if the new nodes are in this case, if new nodes, I'm assuming that new nodes are not coming, only the new links are being formed in between existing nodes, but if new nodes come up, they should also be accounted for in link prediction. So it is true. So link prediction basically here. By the way, am I audible? I can react emojis from here. Like this. I'm audible, right? Let it load and then yeah. So assume I have this network here. I'm just adding 5 nodes, okay? And this is the current network, okay? So assume you have trained an algorithm which predicts links. So what this thing will do, it will start predicting new links in the same network. So it may predict link between this node and this node, between this node, between this node and this node. But if some new nodes come up, say assume this node has come up, so it will also check whether this node should be connected here or here, or like it will check for everything. So assume this node gets connected here. So this is like, this is what? This is new node. New node. These are old nodes. Okay. So this is what you have to do. This is what network link prediction does. What is the range of mutual information? Mutual information is always greater than or equal to 0. It cannot be negative. It is not defined between range of -1 and 1. It is always greater than or equal to 0. It's not greater than or equal to 1. Why is it so? You can read it on Google. It's very easy explanation. In a dendrogram, what does the smaller height of link between groups indicate? The smaller height of link between groups indicate that there are more similarities between groups. Okay, if the height is a lot, because dendrogram is designed in such a way, if the similarity is there, then the height, like link height, is very less. So assume I am drawing this as dendrogram, and I'm placing this node here. So if these nodes are similar, this will be smaller. If these nodes are dissimilar, this length of dendrogram will be longer. Okay. Card similarity score means that influence of nodes through all paths including beyond one hop. Okay, so what is the influence of this node on this node? I can tell easily because it is connected directly. Okay, so if this node is say Amitabh Bachchan, this will be a popular celebrity somewhere, more or less. But that is not the case, because just because someone doesn't follow on someone like a big celebrity like Amitabh Bachchan doesn't mean that they don't just a second, yeah, they don't know Amitabh Bachchan. So if I know this person and this person knows Amitabh Bachchan and follows on Instagram, this means that I also somehow know Amitabh Bachchan via watching his movies or sharing same connections. So this is like an rudimentary link. So card centrality says that information flows not just on one hop but on multiple hops and all the paths. Okay. Which precision measures the number of actual negative links correctly predicted as negative Y model. So that is basically, let me draw the confusion matrix for your clear. So am I audible, guys? Can anyone just unmute themselves? I just want to have discussion about drawing confusion matrix. Like, so anyone can volunteer. It's not going to be an insulting discussion. Don't worry. I just want someone to be a part of this discussion. Or am I audible? Just say yes or no. Anubhav, am I audible? Hello. Okay, I'm assuming I'm audible. Shrikant, hi Shrikant. I am audible, right? Write yes or no in there. Okay, at least you can do that for me. Cool, thanks. So, what a confusion matrix is, assume that I have patients. I have patients with cancer. I have patients. Okay, I cannot write on top. I have patients with cancer. I have 4 patients: A, B, C, D. C has cancer, rest don't have cancer. I train a model which predicts who has cancer. So this model predicts that A does not have cancer, B has cancer, C does not have cancer, and D does not have cancer. Okay, so can anyone tell me which of these 2 wrong predictions can be lethal? Okay, so lethal means that if B does not have cancer and I predict that B has cancer, this means that B will come under some observation. I will start observing B. They will run like the doctors will run some extra tests, and they will try to confirm if he has cancer or not, if or he or she or like they have cancer or not. But assume he has cancer, that this model says no, they don't have cancer. Doctors will let this patient go. Bye bye. Take care. You don't have cancer. But after a few days, doctor will come to know that this person died. Okay. So this is what we do not want. We do not want, first of all, false information. Remember this. We do not want a false information because this is false. And since this if you have cancer, this means that you are positive with cancer. We do not want false negatives. Okay, we do not want people to have false negatives in illnesses such as cancer and all. Okay, now let me give you another example. I have some other set. Assume now I change this from cancer to pregnancy. So A is not pregnant, B is not pregnant, C is pregnant, D is not pregnant. And now I have these results here. Okay, I have some model which tests this. This model will test which one is pregnant. Okay. So not pregnant giving not pregnant is fine. Not pregnant giving not pregnant is fine. If someone is pregnant and this thing gives not pregnant, but ultimately like after some days they will come to know, and it's not a matter of concern because they will be overjoyed. Something happened. Just a second. Like they will be overjoyed with pregnancy, or if they don't want, like they have the choice then. But a person with cancer does not have a choice. But assume this model is saying that this person is pregnant and this is false. So I will write this is false. Okay. But this is positive. So in like movies and everything, and like you might have heard doctors saying that false positives, like the pregnancy test was false positive, means that it was positive and it was false because the person was not pregnant. Now let me write another case. Person has cancer, cancer is detected, or person is pregnant, pregnancy is detected. This means that this is true because it is equal and it is positive. And these are true and negatives. These two are true, negatives. Okay, so these are all 4 cases for confusion matrix. So you write true, false, sorry, 1, 0, 1 actual and 0 1 predicted. So this is 0 0 is true negative, 0 1 is the person is actually pregnant, the person has actually cancer, and this model shows there is no cancer. So this means that it is first of all false and it is negative. Then this thing is false first of all and positive because it has predicted one, it has predicted that someone is pregnant, and this is true positive. This is the confusion matrix which everyone works with generally. Let me just paste it here so that it's easier for you to understand the question. Which metric measures the number of actual negative links correctly predicted as negative by model? So basically there is something called true negative rate, which means that true negative rate is how many true negatives are there divided by total negatives, total negative predictions divided by true negative plus false negative. Okay, so this is basically true negative rate, TNR. I think it was quite a extensive discussion, but you might have come to know quite interesting thing about this one. In link prediction problem, how does the number of nodes in graph typically change? Okay, so typically the nodes generally remain same, but it must also account for new nodes. New nodes can come, but in generally it remains the same. You are basically predicting new links in the given graph only. Jaccard similarity is a local similarity metric because you are checking just the neighbors. You are checking, if I can start computing Jaccard similarity between this node and this node, I will check how many common neighbors they have. So they have one neighbor common, this one, and another one, this one common. So they have two neighbors common. Okay, it is a local similarity metric. Got it? In social network graph, a node A has degree 4, node B has degree 5. Preferential attachment score is the product. According to preferential attachment score, the likelihood score for future link is the product of these two things. Okay, so it will be 20. Just remember this, it's like numerical question. So if node X and Y connected, Y is also connected to Z, and it is likely that X and Z will form connections. This idea is based on common neighborhood because Y is the common node between X and Z. So this was week 7 and it's done. Any doubts in week 7 or any other previous assignment? Okay. Anybody, do you have any, if you have any questions, you are free to ask. If anything you want to ask, because I'm going to start revision from this book. This is like the same thing, whatever you were taught, I will be teaching this thing from this book only because I don't have slides. So I generally prefer this book. Let me connect my iPad. Okay, so I will share my screen here. This will be quite an interesting discussion today. It will take around 30 minutes. Please bear with me. If you have any question, just raise your hand. Then I'll hear the ding and I'll come back to you. Okay, so I'm broadcasting two screens. You can pin the iPad one, because I might have to switch to my display, like PC display, whenever I need to show you something else. So I think chapter 1 doesn't need anything to be discussed. If you have any questions, I will tell you two, three things which are important. So what is a network? Just I'm telling this. Sorry guys, it happens quite a lot in IT. Network issues. Just a second. Let me share my screen. Okay, my iPad is visible. I think so. Something happened. Just a second. Okay, so let me define a network. So whenever you have a network, whenever you have a network, this is it has some nodes. It has some edges. These are edges. So a network G is generally defined using graph, nodes, comma, vertices. Okay. This is the common representation. Just a second. Yeah. So what you have to do is you have to basically just let me know whenever. Just a second. Just a second. Let me pin this. Okay, yeah, that's fine. So what happens is whenever you have a network like this, these edges means these edges. Sorry, DC means these edges. This N means these nodes. This is the basic definition of network. It will be followed later in the course when you are studying network growth models, etc. Then there are types of networks. So I will give you a brief description of types of networks. The first one is unipartite and bipartite. So what is unipartite? If you can partition a graph such that there are no common edges between two portions, that is called bipartite. If you cannot do it, it's unipartite. So assume I make this graph. Okay, and if I say partition here, okay, so this portion has, like, these nodes are connected, but this portion does not have any nodes connected. But since this portion has nodes connected, this means that this is unipartite. But if I assume that I have this network here and I connect everything like this, okay. Now if I divide it here, these nodes are not connected, these nodes are not connected with each other. This is bipartite. This should be clear. I'm teaching this because questions will be coming from this thing. Okay. The third important one is the sign network. I will give you a very good example of this thing. So assume this is India, this is Nepal, this is Pakistan, this is China, this is Afghanistan. India is connected to Nepal, India is connected to Afghanistan, India is connected to Pakistan, India is connected to China, China is connected to Pakistan, Nepal is connected to Pakistan, Nepal is connected to China, Nepal is connected to Afghanistan, Pakistan is connected to Afghanistan. Okay. Everyone is connected, I think so. 1, 2, 3, 4. 1 2 3 4 1 2 3 4, yeah. Now tell me, let's see, India and Afghanistan have a very positive relationship. Assuming India and Nepal also have a positive relationship. Now this gives assumption that India and Afghanistan and Nepal will also have a positive relationship. This is my assumption. Let me make it something like this. My assumptions should be marked in circle. Now India and Pakistan have a negative relationship, and Pakistan and Afghanistan have a negative relationship. This means that negative, India and Pakistan should have a positive relationship. Since they both are enemy of an enemy is a friend. See, the graph is holding a proper structure. Positive, negative cannot exist. There will be some collisions. Let me give you an example. India and China hold a negative relationship. Pakistan and China hold a positive relationship. Now, Pakistan and China, so it's see, negative, positive, negative, positives are existing. China and Afghanistan, now can you tell me how can you compute China and Afghanistan? You can take China and India, Afghanistan. So negative, positive, this one should be negative. If this is positive, this is unstable network. A network which has negative is unstable. A network which has positive, negative is unstable. A network which has negative, positive is stable. Okay, so this is basically a basic of network science. So this means then China, Afghanistan are. I bring Russia here. This is positive. Russia and China are positive. China and India are negative. This means that it is unstable. You don't know when this network like this China influences Russia to become enemy of India, and this positive turns into negative. This can happen anytime. Like we don't know. This is so unstable of the network. Okay. There are some other factors. I'm just telling one factor. I'm just telling based on one factor what could be the possible reason. But there are some other factors as well. So this is what is known as sign network. Quite an interesting. Let me just. This is I think I can do like this. Then we have multi-dimensional graph. So I have some graph here. And I have some graph here. These two graphs are there. Now what see you feel there's some connection between these two edges. You feel there's some connection between these two edges. In that case, it becomes a multi-dimensional graph because you're merging two graphs based on some other parameter. Okay. In multi-dimensional graph, a node cannot have two connections to another graph. It can have just one connection. It's just like a projection from one place to another place, like that. And now the most important one we have is attributed graph. What is the good thing about attributed graph? An attributed graph has nodes with some properties. So assume this is India. And what is India? India is a country. It has 28 states, 29, whatever planning is going on with the division, I don't know. It has some continents, etc. States and it's union territories. And similarly, we have China. China does not work with the concept of states, they are provinces. Okay, so like that. So now each node has some property, and this property can be used to study the behavior of the node. Okay, it can also be used to define the relationship between the nodes. Okay, so now since they are neighbors, they claim property of each other, so they are negative. Russia, say assume this is Russia, they don't share any land area, so they are not neighbors, so they are positive. So you can define it like that. These are some of the common types of graphs. Then you have heterogeneous graph. In heterogeneous graph, like you can combine multiple types of. So now this is a graph of country. If I just start adding people here, so Jinping is president of China, prime minister, whatever, and say assume this is PM Modi is here, and so like it has some ship name INS Vikrant is here. So like now this becomes a heterogeneous graph because nodes start to have different properties and edges also reciprocate those properties. Okay. Now last one we have hypergraph. A hypergraph is that graph where each edge can connect more than two nodes. So assume these two nodes are there, these three nodes are there. How can you connect them via one edge? So this graph has two hyper edges and 6 nodes. And now it has 4 hyper edges and 6 nodes. So this graph can be written like this: G, 4 hyper edges, 6 nodes, 4 hyper edges, like this. Now this is all about the types of graphs, and this is like basics of chapter 1. I won't go to mesoscopic, microscopic, this will be basic things. Now coming to chapter 2. Chapter 2 is all about network statistics. So you have a network. Okay. Now in this network, what you say? You have to find degree. What you can find here is degree. So this is undirected graph. If I add a direction to the edge, it becomes a directed graph. Okay. So you have to find degree. So degree of each node is the number of edges connected to it. So degree of this node is 3, degree of this node is 3, degree of this node is 3, degree of this node is 1, 2, 3, 4, degree of this node is 3. This is for undirected graph. Okay, just bear with me. I have something which is of confusion, but it is like a basic convention. So there is concept of in degree and out degree. So now assume I have a directed graph. I will make a small graph just to make things clear. Okay, so now this graph has in degree. How many nodes, how many edges are incoming? In degree is 1. Okay, and out degree is 2. 2 edges are outgoing. And this one, in degree is 2, out degree is 1. In this one, in degree is what is in degree here? 2, out degree is 1. In degree is 1, out degree is 2. Correct? Am I right? Okay. So see, there's a concept of average degree which I will tell. Just keep in mind, average degree is basically, I'll tell how to compute average degree. don't think so it's discussed here yet. But before that, let me just go to a concept of path and everything. So these are like, this is how you can compute the properties of nodes. These are node properties. Now we'll start computing edge properties. So path is basically an edge property. Okay. So adjacent nodes. First, let me tell you what are adjacent nodes. Adjacent nodes are two nodes which have the common edge. Okay. Then we have the concept of incident edges. Incident edges are those edges which land on a common node. So these two are incident edges and these are adjacent nodes. Okay. Then we have another important concept known as walk. So I take a network. A, B, C, D, E. So let me start a walk from node A to node D. Okay. So walk from node A and node D can be A to B to C. Okay. Then I can go back to A again. And from A to I can go back to E again, and then I can go back to D. So see, here we have repeated nodes. Okay, here we have repeated nodes. So the walk can pass through a same node and edge more than once. Okay, a closed walk is that walk which is basically complete. So a walk from A to A, that is basically A, B, C, A, is a closed walk. Walk length is like how many hops you did. 1, 2, 3, 4, 5. This is 5 walk length. Then we have trail. Like I have not repeated here any edge. Let me just repeat it just for the case. A, B, C, A, B, D. Now see, AB is repeated and A node is repeated, B node is repeated. Now this is a walk proper. A trail is the kind of walk where edge is not repeated, but node can be repeated. So A, B, C, A, E, D. Nodes are repeated, no edge is repeated. So this is a trail. Okay. Then we have path. A path is an open walk, or let me call it an open trail. This is a closed walk. This was a closed walk. This is open walk. A trail can be open or closed based on if it ends on the same node. A path is an open trail with no repeated nodes. So A, B, C, D. This is a path from A to D. This is a trail from A to D. This is a closed walk. This is not a cycle, this is a closed walk because the nodes are repeated. Sorry, not exactly. A, B, C, A, E, D, E, A. This is a closed walk. But A, B, C, A is a cycle. Okay. this should be clear. Distance, ultimately I've told you, distance between two nodes. Distance between two nodes is length of shortest path. So distance between A and D is 2. Distance between A and D is 2. Shortest path is AED. Between A and C is 1. Because directly edge is connected. Okay. Now the other concept is diameter. Diameter of network. So I won't be able to draw the network. I'll just tell you the exact formula how we compute. So what we do is, you take all pairs of nodes, all pair of edges. You take all edges. You take AB. Let me just minimize it. You take BC, you take CD, you take DE, you take EA, you take AC, like that, all the edges, and then you compute the distance between these nodes, and then you take the longest value. Okay, so longest value like A and D, can this become 1? No, because A and D is connected via E only. Like minimum can be 2. A and C can be 1, A and B can be 1, A and E can be 1, but A and D, B and D can be 1, but B and E is 2. Okay, D and C is 1, so every other node is connected just via one edge, but A and D, B and E, C and E is connected via two edges. So the largest value is 2. So diameter of this network is 2. Okay, and this is quite intuitive. Actually, you are seeing what is the largest possible path a node can take to reach in shortest time is 2. That is the diameter. Okay, so this is all the concept about these things. Then you have density. So density of network is total number of edges divided by total number of possible edges. Total number of edges you can count, and possible edges is number of vertices C2. Okay, so if you have two nodes, that is 2 cross 1 upon 2 cross 1, there can only one edge possible. If you have 3 nodes, you have 3 cross 2 by 2 cross 1, then only 3 edges possible. If you have 4 nodes, 4 cross 3 cross 2 cross 1. Okay, this is 12 by 2 is 6. 6 edges are possible. Okay, so in a graph, if you have like 4 nodes, 2 edges and 6 edges are possible, density is 0.33. This is how you do it. Then you have clustering coefficient. Hold on a second. Let me have some water. So I will tell local clustering coefficient only first. Local clustering coefficient. Okay, so assume, since this is a local clustering coefficient, you have to find it for a node. So local clustering coefficient for a node is basically number of edges between its neighbors divided by number of edges possible between neighbors. So this is again NC2. So assume like I have this network here. So I have to find clustering coefficient of this node. So this has how many nodes, neighbors? This one, this, let me just do double circle. This one, this one, this one, this one, and basically all the nodes. So it has basically all neighbors. Okay. Now if I remove this node from this graph, okay. So how many edges are between neighbors? 1, 2, 3, 3 is this one. 3, 4, 5, 5. And there is again how many nodes are there? 1, 2, 3, 4, 5. This is 5 C2. This is 5 upon 5 4 20 by 2, 10. So local clustering coefficient of this node is 0.5. Global clustering coefficient is different. Global clustering coefficient is for a graph. So global clustering coefficient is computed for a graph, which is number of closed triples or triplets divided by total number of triplets. So a triplet can be, let me just show you. Assume I have this network. This is 1, 2, 3, 4. Okay. So total number, there is only one triplet closed, because if I write 1, 2, 3, what happened? Just a second. Any doubts? Okay. So if I write 1, 2, 3, this is connected, right? 1 is connected to 2, 2 is connected to 3. If I write 3, 2, 1, it's connected again. 3 is connected to 2, 2 is connected to 1. Okay. If I write 3, 1, 2, it is connected again. Okay. So these are all open triplets. Sorry, closed triplets. 1, 3, 2 is also there, I think. 1, 2, 3, 3, 2, 1, 1, 3, 2. Okay, so this is means that like there's only one closed triplet. Now total triplets, I mean closed triplet also triplet. Now this is also a triplet. 1, 4, 3. Because 4, 1, 3 can be done, 3, 1, 4 can be done. But 1, 4, 3 cannot be done, so this is an open triplet. Again for this one. So this is 1 by 3, this is 0.33. Okay, so this is all about global clustering coefficient. Okay, so this is the basic of chapter 2, and the rest of chapter 2 what we will do in the next class, because I think that strength is very low today. In next class we will do chapter 2, the remaining like clustering and low network centrality and other things. Okay, and chapter 2 will complete, and we'll start with chapter 3, and we'll finish half of chapter 3 in next class, and then we'll in the next class we will do the remaining half of chapter 3 and chapter 4's first half. So this is how we will do, because finishing 2 chapters will be quite hectic for you guys to study as well. If there's any doubt, just let me know. Do you guys have any doubts? Okay, so in that case, if there are no doubts, let's drop and let's meet next week. Thanks a lot. Bye bye guys. Take care. Have a nice weekend.